In this series of videos, we're going to be looking at rational functions, and one of the techniques we're going to use is that of partial fraction decomposition. In order to use partial fraction decomposition, we need to begin with a proper rational function. A proper rational function is characterized by having the degree of the numerator less than the degree of the denominator. And if we don't have that, then we need to use long division in order to ensure that we do. Once we do, the idea of partial fraction decomposition really is based on adding fractions. Let's consider, for instance, 2 over x plus 3 plus 1 over x plus 5. In order to add these two fractions together, we would get common denominators. So we'd multiply the first fraction by x plus 5 over x plus 5, and the second one by x plus 3 over x plus 3. Distributing and collecting like terms in the numerator will give us 3x plus 13, and then the denominator turns into x squared plus 8x plus 15 when we multiply. What partial fraction decomposition asks us to do is this process in reverse. Starting with 3x plus 13 divided by x squared plus 8x plus 15, we would set up two fractions, one of which has a denominator of x plus 3 and the other has a denominator of x plus 5. Giving each of these fractions an unknown numerator, we set this up as a over x plus 3 plus b over x plus 5. Then, working as though we were adding two fractions, we would again get common denominators by multiplying the first fraction by x plus 5 over x plus 5 and the second by x plus 3 over x plus 3. This would result in a times the quantity of x plus 5 plus b times the quantity of x plus 3 divided by x squared plus 8x plus 15. I didn't write what's on the left-hand side, and I'm going to now. 3x plus 13 divided by x squared plus 8x plus 15. And the strategy I'm going to promote is if we know that the denominators match, and we have two fractions that are equal to each other, then it must be the case that we can form an equation just of the numerators. Or if you like, we can multiply both sides by the least common denominator, thereby clearing all of the fractions. Either way, we have an equation that looks like 3x plus 13 is equal to a plus b, that quantity times x, plus 5a plus 3b. Comparing like terms on the left and on the right, we see that we can form an equation 3 is equal to a plus b, and another equation 13 is equal to 5a plus 3b. To solve this system, I would multiply the first equation by, say, negative 3. So I have negative 9 is equal to negative 3a minus 3b. Add that to the second equation, 13 equals 5a plus 3b, thereby eliminating the b's. And we get that 4 is equal to 2a, which would mean that a is equal to 2. Since a plus b is equal to 3, we would know that b is equal to 1, and we would be able to recover our fractions. You see, we had a over x plus 3, so 2 over x plus 3, plus b over x plus 5 with b equals 1 gives us 1 over x plus 5, which is, of course, what we started with, so we knew the answer to this one. The point is, though, we're going to be doing this with fractions where we didn't know where they came from. That was a fairly fast overview, but we'll be exploring this more as the videos go on. We're going to look at possible factors in the denominator because, folks, we're going to be looking at denominators like the one we just saw, x squared plus 8x plus 15. And this was factored into x plus 3 times x plus 5. The type of factor that we have in a denominator is going to determine what our numerators are going to look like. There are four possibilities. Case 1 is one in which we have, say, stuff. The numerator is not the point right now, so I'm just looking at the denominator, over x plus 4. Imagining that x plus 4 is one of the factors in the denominator. I'd like to point out that x plus 4 is a linear factor. If we see a factor like this, then we will set up a fraction with a denominator of x plus 4 and a constant numerator. We need a constant numerator because we're setting up proper fractions. And if the denominator has a degree of 1, the numerator should have a degree of 0. The second case, which we'll call case 2, is we have stuff in the numerator over, say, x plus 4, the quantity cubed, for instance. This is characterized as a repeated linear factor. Even though it's x plus 4, the quantity cubed, what we focus on is that we have a linear base. With an exponent of 3, I would need to set up 3 fractions, one of which has a denominator of x plus 4, one has a denominator of x plus 4, the quantity squared, and one has a denominator of x plus 4, the quantity cubed. Because the denominator has a repeated linear factor, our numerators should again be constants. And so my constant numerators will be a, b, and c. Now, as far as having 3 instances of the x plus 4, one of which is just x plus 4 by itself, and then x plus 4 squared and x plus 4 cubed, I would appeal to the idea of the fraction 7/8 can be expressed as 1/2 plus 1/4 plus 1/8. Each of these denominators has a base of 2. In the first case, it's 2 to the first power. For 1/4, it's 2 squared. For 1/8, that denominator is 2 cubed. Notice that the result of adding those together, 7/8, has a denominator of 2 cubed. Therefore, we should consider the base with every possible exponent, starting with 1, all the way up to the exponent that we actually see for the repeated linear factor. In case 3, we consider something like stuff divided by x squared plus 4, supposing that's one of our factors. X squared plus 4 is a prime quadratic, or it's referred to as an irreducible quadratic. If we see such a denominator, then we will set up a fraction with the denominator of x squared plus 4. We want a proper fraction. I only want the degree of the numerator to be 1 less than the degree of the denominator. Since my denominator is a quadratic, I want a linear numerator. The most generic linear we can have is something that looks like ax plus b. Case 4 is that of a repeated irreducible quadratic, something like a denominator with a factor of x squared plus 4, the quantity cubed. As before, we would set up 3 fractions, one of which has a denominator of x squared plus 4, one has a denominator of x squared plus 4, the quantity squared, and one has a denominator of x squared plus 4, the quantity cubed. Again, the base of the denominator in each of these cases is quadratic. Therefore, we need, again, linear numerators. So our fractions look like ax plus b divided by x squared plus 4 plus cx plus d divided by x squared plus 4, the quantity squared, plus ex plus f divided by x plus 4, the quantity x squared plus 4, the quantity cubed. Here we have unknowns a, b, c, d, e, and f. This would be kind of a bear because we would need 6 equations to determine what the 6 unknowns are.